All right, everybody. Welcome to the Green Bank Observatory. Thank you all for coming out this afternoon. Um, really excited to introduce our lecture that will be getting started here in just a couple minutes. I wanted to make a couple of quick announcements. First of all, my name is Angela. I'm the Public Outreach Manager here at the Science Center. So if you are ever interested in a tour or an education program, I can help, my team can help you set that up. We have a few events coming up here soon. So if you are in the community, if you've heard about our SETI tours and you're interested, they'll be starting up in April. And those are seasonal, so they run through September. We also have an event coming up. If you've heard about the solar eclipse on April 8th, that slide is somewhere in here. I don't know if it'll, yes, there we go. So on April 8th, which is a Monday in the afternoon, we have I forgot what percentage we are, but we're over 90% of totality. So it's going to be a pretty great event. So you are welcome to come join us here at the observatory for the afternoon, and we will have eclipse glasses available. If you have your own, feel free to bring them. But that should be a lot of fun. So please help us spread the word. Some of you also may know about an annual event that we host, the Space Race Rumpus. So last year was the first year back since COVID. So we're slowly trying to ramp back up again and get our numbers back up for that. So if you're excited about biking and want to join, there's something for everybody. So check out the website and you can register for that. So those are the announcements. We will have a reception after the talk, so please feel free to stick around and enjoy the snacks and some conversation with our speakers. I'll have the gift shop open. I may not be right there at the register, so if you're interested in the gift shop, just ask around for Angela, and I am happy to help you out in there. And I think with that, I'm going to turn it over to our acting director, Dave Freyer, and he will introduce our speakers.
Thank you, Angela. Welcome, everybody. It's really nice to be able to host a prize lecture. The Shaw Prize is a big deal. So congratulations to both Maura and Duncan for receiving that. That's a international, I mean, that's up there sort of with the Nobel laureate. I mean, that's a big thing. I mean, that's really awesome. They, they got embarrassed in Hong Kong in November of last year. So it's a 2023 award. We're recognizing them here today. We're happy to have them here. We consider them part of our extended family here at Green Bank. So Maura, you got your PhD back in 2001 at Cornell and been at WVU since 2006. Duncan, they're a married couple. I don't know if this is the first Shaw Prize that was handed to a married couple or not. It might be. You're pioneering in so many ways. Duncan, he got his PhD in 1994 at the University of Manchester, and has also been at WVU faculty since 2006. I'm going to read the contribution. This came off the Shaw Prize page, So I was going to read a little thing so I get this right. So the Shaw Prize in Astronomy 2023 is awarded in equal shares. So there's a cash award. I won't get into the details of that, but it's pretty significant. To Matthew Bales, this a guy down in Australia, director of the Australian Research Council, ARC, Center of Excellence in Gravitational Wave Discovery, Duncan Lorimer, professor, and at the time interim chair, now Maura is the chair of the Physics Astronomy Department in West Virginia. Duncan is Associate Dean for Research at Eberly College of Arts and Science at West Virginia University, and Maura McLaughlin, and Eberly, I'm in between reading now. I have to close without my glasses or far away with my glasses. Family Distinguished Professor at the Department of Physics and Astronomy and Director of the Center of Gravitational Waves and Cosmology at West Virginia University. And this award is for the discovery of fast radio bursts, which they will get into and give a little bit of the background on it. It's a big deal. I mean, gosh, I guess it's been about 15 years now, like 2006, 2007, they were discovered, and we didn't really know what was going on. And it took a while we still don't know exactly what's going on, and that's the whole point of their talk. But the Shaw Prize itself, it's been around for 20 years, and it's gaining fame and recognition. And it was put together by Run Shaw and his wife, Mana Shaw, and they're from Hong Kong. And the prize is to the goal, like sort of like its mission statement, is to inspire and recognize imaginative individuals committed to scientific research and to highlight their discoveries. They give an award in astronomy, and also in life science and medicine and mathematical sciences. So those are the three areas that they focus on. And we're welcome to have the two people that received it two of the three that received it last year in astronomy. So I'm just going to hand the floor over to both Duncan and Maura, and you guys figure out how you want to tag team this.
Yeah.
Okay. You have a plan. Okay. Well,
all right, thank you so much, Dave, and it's great to be here, and really, really excited to tell you this story this afternoon. Where, as Dave mentioned, back in 2006, 2007, as we were just making this discovery, one of the first places we announced it was here at the observatory. So it's really nice to be back here and tell the story to you all. So we're going to be talking about these fast radio bursts in some detail this afternoon, but I wanted to start off fairly generally. We're at a radio observatory, so it seems very fitting to be talking about the radio sky. It's always interesting when I think about this. When we look out at the night sky with our eyes, just about everything we see is a regular star. Bigger or smaller than our sun in our Milky Way galaxy. When you look out at the radio sky, though, it's quite different. So here is the skyline of the Green Bank Observatory just outside of us. And this is an image that was made if your eyes were sensitive to radio waves of 5 centimeter wavelength. So very different to the optical light that we see with our eyes. So it's a completely different view of the universe. And so what you're looking at now, all those dots in the sky, they are predominantly galaxies, not stars. So it's a very, very different view of the universe. You're looking at objects that are generally much farther away and much more massive. You see some of these extended objects as well. Some of those are supernova remnants from the explosions of massive stars in our galaxy, and they radiate in the radio. And so through radio astronomy and then across the electromagnetic spectrum, using telescopes, both on the Earth and in space, we're able to build up this picture of the universe with all these different contributions, and also with gravitational wave astronomy. I won't get into that today, but astronomers are constantly pushing the boundaries of how they study the universe. So I want to play you, we're talking about fast radio bursts today, and I want to play you the sounds of what they might sound like if you digitize the signal. So what we're going to hear is just a short clip, and it's mostly going to be noise. You're going to hear this background hiss. That's actually intentional. That noise is coming from the sky and the electronics in the receiving system. And then you'll hear the bursts, and you'll hear them as chirps. You'll hear the highest pitch first, and then the lowest pitch after that. So let me just see if I can play it here. So you hear those chirps. They're of different intensities. So those were simulated signals, but that's basically how they would sound if you converted them into audio. What we're trying to capture there is the fact that the highest frequency radio signals are arriving first to the Earth, and the lowest frequency radio signals are arriving a little bit later. And so this is a really key point, that space is not a complete vacuum. It's not totally empty. It has gas floating around in it in between the stars. And in particular for the radio signals, there are free electrons just floating around in space that form what scientists call a plasma. And that plasma acts like a prism to the radio waves. It changes the speed at which they propagate depending on their frequency. It has a different refractive index. But the highest frequency radio waves travel faster through that plasma than the lowest frequency ones. And so when you look at it schematically here, if you've got a graph of radio frequency versus time, These are the highest frequency waves, and so they're scrunched together. They have shorter wavelengths. They're hitting this cloud of electrons, these E's with minus signs, representing these little electrons that are floating around in space. And then the lower frequency ones are traveling slower. So you get the pulses delayed there. And then you can see the actual real signal that we're talking about. This is the first fast radio burst that we found. So what you're looking at here is just half a second of data. So it's just a tiny, fraction of the information coming from the sky day after day. We think of the universe as a very ephemeral and unchanging, but what we're finding here and in many other branches of astronomy is the universe is dynamic on very short timescales. So this particular signal only lasted a few milliseconds, and the signal itself was received by the telescope at the higher frequency. Here it is, it arrives first, and then the lower frequencies arrive later and later. If you have a driver's license with you, you might want to look at the back of it. You'll see zeros and ones there encoded on your little barcode. That looks a little bit like the background noise in the detector there. We digitize the signals in a similar way to the way they're digitized on your driver's license. Anyway, that's just an interesting side issue. But the pulse itself is clearly detected, and it was unlike anything we'd ever seen before. So I'm just about to pass the baton over to Maura now. But what we're really going to focus on in this talk are radio telescopes. They come in many shapes and sizes. Of course, being in Greenbank, West Virginia, you see the beautiful dishes outside that are in many different designs. This is the instrument that you're looking at now. This is the instrument that detected that pulse that we just saw. It's the Parkes Radio Telescope in New South Wales. It's about a 5-hour drive from Sydney, and it's been in existence since the early 60s. One of its early claims to fame is that it brought back the signals from the Apollo 11 moon landing. So if you've seen the movie The Dish, or get the opportunity to see that, it's featured in there. It's a really great movie. And for radio astronomers, it's been just a fantastic instrument over many years and still is in operation and in high demand today because it can see the southern sky. We see a lot of interesting objects from here in Greenbank, and we see about 80% of the whole sky. But there's a bit that we're missing that we would really like to see here, where the central regions of our galaxy and Parkes, that just transits overhead there down in Australia. And so they get to see that really in fine detail. And Parkes has been great for finding pulsars and many other radio sources over the years. And so I'm going to hand things over to Maura now, and she'll sort of go back and talk about the pulsar side of things, which is really important.
Thank you, Doug. Yeah, so whenever you build a new type of telescope that's sensitive to a new type of light, there are surprises, right? Every time in astronomy, someone has built radio telescopes or X-ray telescopes, new sources pop up. And so this is the story of radio astronomy, sort of like in the mid-1900s, the first radio telescopes were built. And initially, those telescopes weren't sensitive to short timescale phenomena, right? They just made maps of the static radio sky. And then in the mid-1960s, astronomers became aware of a type of source called a quasar. It stands for a quasi-stellar radio source. And these things looked like just points on the sky, kind of like stars, but they varied. Their intensities, their radium intensities kind of went up and down and up and down. And this was thought to be due, and we know now it is due to interstellar scintillation. So when you have a tiny radio source, a small radio source on the sky, the radio waves interfere with each other as they travel from the source to Earth. And this results in brightening and dimming, kind of like twinkling, right? If you see like stars with your eyes, you see them twinkle. This is like radio twinkling. Okay, so these quasars were a really big, new, exciting new phenomenon. And at that time, Jocelyn Bell, her picture will be on the next slide, was a graduate student at Cambridge in England. and it was mid 1960s, 1965, 1966, and she wanted to get her PhD, and her advisor, Anthony Ewish, said, let's study these quasars. Let's monitor this sky on short timescales so we can really follow this like brightening and dimming due to scintillation. And so Jocelyn went and built this radio telescope. It doesn't look like a radio telescope. It doesn't look like the Green Bank telescope or the 20-meter, but this is a radio telescope. It's basically a field of radio antennas. And it was sensitive to shorter timescale phenomenon than any telescope had ever been sensitive to before, like much shorter than they even needed to be sensitive to study quasars. And this is a really important lesson, right? Whenever you build something that's sensitive to a new regime, you're going to find something new. And Jocelyn did find something new. So this is a picture of Jocelyn doing her PhD research, and she looks really happy because she made a really unexpected discovery in her data. Let me see if there's a, I can just kind of, actually, I think I can use this. Yeah, okay, I can use the cursor. Cool. Yeah, so what Jocelyn would do is the telescope just sat there as the sky drifted overhead, right? And so she would take data, which measured like the radio intensity of the sky with time, and she would take data on a pen chart recorder. There's still a pen chart recorder here that students use on the 40-foot telescope for science experiments. They absolutely love it. It's really fun. And so as the sky drifted overhead, the intensity was recorded. I need to turn this the right way because I'm getting, oh, there we go. The intensity was recorded like this. So this is basically like intensity versus time. And you can think of time as position on the sky because we're observing the sky as it like drifts overhead of the telescope. You can see it looks pretty scraggly. So this is the radio noise that Dunk was talking about. I can't seem to manage this stupid cursor. There we go. Yeah, so this is like the radio noise that Duncan was describing, right? That hiss, that shh, right? But you can see a couple signatures in this plot. So here's some like scraggly stuff here that sort of peaks above the noise. Here's some stuff here. And Jocelyn noticed this thing right here, which didn't look like interference. So this is some interference, some human-made interference, right? From someone's spark plugs or, you know, who knows, a TV, a radio signal. And this other signal looked kind of like it, but not exactly. And she was really intrigued by this, but everything happened so fast. Like all of this signal happened in a tiny little blip of the pen chart recorder. This was, as you can see, August 6th, 1967. She talked to her supervisor and said, hey, this is really cool. What can we do? And so they adjusted their recorder to move way faster so they could get better time resolution data, right? So they pushed the paper through faster so they could get better time resolution data. And they got something that looked like this. And I can only imagine how excited she was when she saw that this source that she observed up here, and it kind of just looked like a kind of bunch of noise, actually turned out to be a periodic radio source. So these pulses are negative going. They're really positive intensity, but the way the pen chart recorder worked, they look negative, but these spikes are actually brighter than the noise. And they look really periodic, right? They're very, very equally spaced, and the period was about 1.3 seconds. And this is the first pulsar that was discovered. And you'll see why this is important, because the way we discover pulsars has kind of led to the discovery of the first fast radio burst. So this is the story of the discovery of the first pulsar. So you can see these are single pulses spaced periodically. They didn't know what to make of this at first. The first one was nicknamed LGM1 for Little Green Man 1. And the reason they nicknamed it that is because this was such a short timescale phenomenon. And people didn't think stars could be small enough to produce a signal that short, right? You need a really small thing to produce a signal with a period of 1 second. That's really tiny. And so people thought maybe this could be like a signal from an alien civilization, from a planet, from something tiny. So speculation went on for some time, you know, a few months after Jocelyn and her supervisor, Anthony Ewish, made this discovery. And then in 1968, there were pulses discovered, just like the pulses from that pulsar and a few others that they had found using this Cambridge array. Pulses were discovered from the Crab pulsar. And this pulsar was located in the Crab supernova remnant, right? So radio pulses, just like those other ones, were found from a supernova remnant. Duncan mentioned these in that first image, right? These are these like beautiful nebulous radio structures. And these remnants are produced when a massive star explodes. And these pulses were detected coming from the position of one of these remnants. So astronomers at the time said, aha, these pulsars are born in the explosions of massive stars. They must be a special type of star called a neutron star that's produced when a massive star explodes, right? And these neutron stars are really cool objects, tiny, 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 the size of a city. They can rotate very rapidly, hundreds of times a second, high magnetic fields, really exotic objects. So that is the story of pulsars, how we know what they are. And now I'd like to kind of shift things a little bit and talk about another kind of cool aspect of this Crab pulsar, which will lead us into fast radio bursts. So if you look at like this image here and these pulses at the bottom there, they're very periodic. And you also notice they're roughly equal intensity, right? So every pulse has roughly the same brightness as the other pulses. Okay, now look at these Crab pulsar pulses. There are some that are humongous, really, really, really bright. There are stretches when you don't see any pulses at all, and then you'll see another really bright pulse, no pulses, another really bright pulse. We call these giant pulses. So the Crab was discovered through its occasional, very rare, but very bright giant pulses. So this is a special type of pulsar that emits a different kind of pulse, like really, really bright pulses. Okay, now, because the Crab was discovered that way, this got astronomers at the time really excited about looking for other sources of really, really bright, narrow radio pulses, like those ones detected from the Crab pulsar. And there was a lot of effort that started around the early 1970s, searching for other sources of what we would call single, so isolated, dispersed. So what Dunk talked about, they would follow this characteristic thing in frequency, pulses. And these are some pictures of some of the people who pioneered this, you know, starting in the early 1970s. And they were searching for all sorts of things. There were, you know, not just pulses from pulsars, but pulses from very exotic things like black holes collapsing or two neutron stars smashing into each other. There was a lot of activity, you know, after this Crab discovery in the 1970s, and then it kind of waned. And people gave up because nothing was found. No more pulses like this were found, aside from a few other pulsars that kind of looked like the Crab. People kind of stopped looking at data this way. And then I was a PhD student at Cornell in the mid to late 1990s, working with Jim Cordes. This is a picture of me and Jim Cordes and that Shami, Chatterday, Shami, you know Shami. This is like a really old photo in Jim's lab at Cornell. And we decided for my PhD thesis to kind of like bring back this method of looking for pulsars through these single pulses. Like people had kind of stopped doing that because there are much more efficient ways to detect normal pulsars than this. And so we decided to look for pulsars through these single pulse searches. And in particular, we started targeting other galaxies, looking for pulsars like the Crab, because maybe we can't detect them the normal way, like through their kind of average emission, but maybe if they're really far away, we could detect the occasional really bright pulse, right? Even though they're super distant. So for my thesis, we focused on searching for pulses in other galaxies, trying to detect these very bright, narrow pulses from things like the Crab. Okay, anything else I want to say about this? Okay, so yeah, so this is the kind of plots that I made for my PhD thesis and when I was a postdoc. These are super boring plots. I like showing this stuff at public lectures because I think, you know, at least before I knew about pulsar astronomy, I imagined all astronomers did were like look at like beautiful images, you know, but like this is what we do when we search for these single pulses. So what you're looking at here, that y-axis is dispersion measure. That basically translates to the amount of sweep, right, that a signal will experience as it travels from the source to the Earth, right? So if it has a big sweep, that means it's coming from really far away because it met up with a lot of electrons. If it has like just a little sweep, that means it's coming from really nearby because it didn't interact with a lot of electrons. So the top of that axis is like very far away stuff. The bottom is nearby stuff. So 0 means coming from Earth. 700 means coming from really far. And the x-axis here is time. I don't know why we lost the units on this, but this is about a half an hour observation. This is data from the Parkes telescope in Australia. This is a plot that I made when I was a postdoc at the Jodrell Bank Observatory, and I decided to look at this pulsar survey to see if we could find like any new stuff that had been missed before. And we found a whole bunch of stuff like this. So this is a really weird pulsar where we see 3 very bright single pulses. You can see they're all about the same DM, which means the same distance, which means they're real. They're not interference, they're not coming from Earth. And you can see 2 of them are closely spaced, and then there's another one like 15 minutes later, and nothing in between, right? So this is not a normal pulsar that's going boom, 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 like Jocelyn's original pulsar. This is a weird pulsar that's going boom, 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 and it's quiet in between. So this was a new kind of source. This was really exciting. We found 11 of these in our first pass through the Parkes survey, like 11 of these new kind of sources. And so because of this, this kind of, like inspired a resurgence of looking at data using these single pulse algorithms to see like what else we might find. And I think I am going to pass it off to Duncan now, and he will tell you what we did find.
All right, so now we're getting to around 2006, 2007, when Maura and I arrived at West Virginia, where we've been ever since. You can see a picture of us down there in front of the GBT. That first summer, I think that was, with our first son, who's now 18 years old, just about to go off to college. But back then we didn't know what to expect. And,
didn't know how to hold
didn't know how to hold baby that way. We soon learned. Anyway. So one of the things that we were trying to do as new professors is hit the ground running and give students research opportunities. We didn't have a lot of data with the GBT just yet. We've gotten a lot since then, but back then we wanted to just start students working on projects where data already existed. And so as Maura said, there was a lot of interest at that time in looking for pulses in archival data sets that perhaps had been missed by these other techniques. And so one particular data set we got really excited about was in the looking for pulsars in the Magellanic Clouds. Now, has anyone seen the Magellanic Clouds? Seen those? A few of you have seen those, been down to the Southern Hemisphere. It's definitely a thing worth doing if you get the opportunity. They really do look like clouds in the night sky, but they are, in fact, satellite galaxies of the Milky Way. So they're great places to look for these bright individual pulses. We might be able to see those. And there's indeed 1 or 2 sources that emit pulses in that way. So we thought we'd look for more of them using this new software that Maura and others had developed. And so we engaged the efforts of an undergraduate student at the time, Ash Markovic, who wanted to search some data, and we looked in the Magellanic Clouds for these signals. So here's another example of one of these plots that Maura was showing. So this is an actual observation from the survey that we were analyzing. So we had thousands of these to look through, all these different pointings with the Parkes telescope. So you're looking at here, now the time axis has got units on it. And so you can see it's actually 2 hours of, over 2 hours of data that we're looking at. And you can see a steady stream of pulses at a dispersion measure of around 100. Just to give you a rule of thumb, a dispersion measure of 30 is about 3,000 light years away, something like that. So this particular one is a little bit further out than that, but it's consistent with a source in the Magellanic Clouds. And it's actually a pulsar that we already knew about. So it was a good test that the system was working. But then one day Ash came into our office and showed us this signal here, where and we've just kind of zoomed in on the highlight of the plot that you can see on the right there, where we see this incredibly bright signal, and the size of the circles here is proportional to the intensity of the radio signal. So you can see it getting brighter and brighter as you line up the pulses across that sweep, and you get the alignment perfectly so that you see the pulse. And that particular one comes at around a dispersion measure of 375, much greater than the ones that we've been seeing for the Magellanic Clouds. And it was actually higher than we were expecting to see. If you look at the picture on the left there, you can see why we were really became even more intrigued about this. We'd seen this incredibly bright event, but then we looked on the sky to see where we were actually pointing. So the map there in the background shows you the small Magellanic Cloud, the smaller of those two galaxies. And then the arrow is pointing to the position that the telescope was actually looking at. And the telescope had a 13-pixel camera. Your phones have thousands and thousands of pixels. We had 13 pixels on the telescope, which was great. It allows us to look at 13 different spots in the sky at once. And you can see the little footprint that it makes on the sky. And those circles that have been highlighted are where we detected the burst. It was coming from multiple positions on the sky, and we were able to triangulate it to a point that was about 2 or 3 degrees away from the Magellanic Cloud itself. So we basically got this bonus observation looking out into the distant universe where we'd seen this just this singular event. So it was an unexpected signal, very bright, at an unexpected sky position. So something that unlike we'd ever seen before. And that summer of spring into summer of 2007, we were at Green Bank writing this paper. It was a great time to be doing that. Second son was born in the middle of that summer. There was lots of exciting things happening. And the paper came out in Science the fall of that year, and you can see the plot that we made from the discovery that shows that individual pulse. We ended up looking for 90 hours. Matthew went back to the telescope for 90 hours looking at that spot in the sky, looking for follow-up bursts, and we never saw another one. And so the implication was that we'd seen something new, but it was perhaps just a one-off event. Now, as astronomy has many examples of this. You find the first source, but then you often see more and more fainter examples of the same thing. So the implication was that this was the precursor of a new population. When we made some initial estimates as to how far through the universe it actually was, it turns out to be several billion light years away. So really a very distant source. And that was informed by estimates of how we think the electrons are distributed throughout the universe. So when you make those estimates and figure out how much energy was actually released, it's something like what the sun puts out in about a month, we were seeing in a few milliseconds. So it was really unlike anything we'd ever seen before, much, much brighter than those crab giant pulses that Maura was showing, and something entirely new. And I always like to have a picture in my mind's eye about what we're looking at in astronomy. And here's a good example of that here. This is basically what we were thinking of back in 2007. And the idea that we were proposing is that we'd seen something from this distant galaxy on the left here that's traveled 3 billion light years across the universe. And we happen to be looking in the right spot at the right time. And I'll just talk you through this little plot down on the bottom here. You can see this is the pulse at various stages throughout its journey. So the pulse is traveling pretty much at the speed of light. It takes it 30,000 years to leave its host galaxy, let's say. And it's picked up a little bit of dispersion over there from the host galaxy. So that's it when it leaves the galaxy. Then it travels across the universe for the next few billion years. And it picks up a lot more dispersion from the electrons just in free space, just because there's a lot of space it has to travel through. And then the last 30,000 years or so, it travels through the Milky Way, and that's what it ends up looking like at the end. So that sweep that you see really is a fingerprint of its journey through the universe, like kind of like a passport getting stamped on the way through various parts. So it's perhaps passed through another intervening galaxy. So there's a lot of information in just that few milliseconds of data. So really exciting stuff. We made some proposals about what it could be. We estimated its energy, as I told you, and it was unlike anything we'd seen before. It was very narrow. It had a short duration. That meant, as Maura said before, it had to be something small, like the pulsars are small objects. This probably had to be something small, like something coming from the surface of a star. A whole galaxy couldn't produce something that was varying on a timescale of a few milliseconds. That's too big for that. So it's something what we call small and coherent. So so it allows the organization of radiation in a single particular direction. Perhaps it was just a one-off event. So we put up some ideas. Perhaps it was the inspiral of two stars, or the explosion of some sort of extremely violent supernova explosion, or a really giant pulse, or something else. And so the burst, that original burst has, for better or for worse, been named after me, and it sort of slowly made its way into the zeitgeist over the years. And there's even a instrumental German rock band that they call Lorimer Burst, and they have it's a trio there that you can see. They have an album out called Dispersion. My sister-in-law is from Germany, and she went to see them at a gig about a year ago. And she after the show, she introduced herself and told them who she was, and they went like, so they gave her a copy of the album, and they're worth checking out. They also make their way into the literature. There's this book about relationships over there on the left. This burst has traveled billions of light years across the universe, and so you can resolve any issues that you're having in your own life. Things like that. I think it's probably time for me to hand back to Maura, and she's going to be telling you about what happened next.
How we found out about the relationship book. I think a friend of mine read it, and they were like, I'm reading this relationship book with my husband, and the Lorimer burst is in there. As Duncan said, when astronomers, or well, any scientist really, when you find something new, you assume there are more of them out there. And so you start a dedicated search to find more of them, because you want to know, is this thing unique? Is it part of a population? If it is, like, what are the different properties? So we and lots of others, after this first started looking for more. As Duncan mentioned, we spent a lot of time looking like right at that position on the sky, making plot after plot like the ones we showed you, trying to see if we could detect another burst from that position. And we looked for really faint ones, right? Because we knew it was there. We looked for really faint things, couldn't see a single thing in 90 hours of observing, and even more after we published that paper. So no bursts were found. We also started looking in other surveys. So that Parkes multi-beam survey that I showed you the plots from, that I looked at during my postdoc, we looked at that survey. We didn't see any in there. Everyone started looking for these in all the pulsar data that were being taken, and no one found one for a while. So we had published our paper in 2007, and it wasn't until almost 2012 when similar things were found. And there was a paper led by Sarah Burke-Spillar, who's actually a faculty member at WVU now as well, which is kind of a nice full circle thing. And she found stuff that looked like the Lorimer burst, but not exactly. So this plot here shows what Sarah, who worked with Matthew Bales, he was her PhD supervisor. She was a PhD student at Swinburne University in Australia. You can see what she saw here. So she saw a signal. It showed this dispersion sweep, right? So it was, appeared earliest at the high frequencies, appeared later and later as you got to lower frequencies. So that looks a lot like the Lorimer burst, but it's kind of patchy. It just shows up, it's really bright here, it's bright up here, it's not detectable across the whole frequency band. So this was pretty weird. They called these things peritons, and I think a periton is like a deer that an animal that looks like a deer but is actually human. So it's like a masquerading mythical creature, right? And so the reason they called them this is they thought that these were not astrophysical signals. And there's a lot of reasons for that, but they were seen all over the sky in all the beams of that multi-beam receiver, not just one. So they thought these weren't real. These were some kind of human-made thing, but they looked a lot like the Lorimer burst. This was very upsetting to us because then this paper was published and a lot of people started saying, well, that Lorimer burst wasn't real either because it looks like this thing and these things aren't real because they're detected everywhere, all over the sky. They have similar dispersion measures even, like that DM number was really similar. So we were pretty dejected and not quite sure, after this, whether these were real or not. Duncan never gave up faith in the Lorimer burst. He always believed it was real, 100%. But there were a couple meetings where someone would ask, like, who in the room believes the Lorimer burst was real? And out of like 100 people, like it was Duncan, like 2 people who raised their hands. And even I started doubting because we looked at so many other surveys and did not see a single other one. So even I started doubting, was this thing real? It looked real, but maybe it was just very convincing radio frequency interference. But then, fortunately, a paper by Dan Thornton was published. Was this 2011 or 2012? 2012? 2013? Okay, yeah, we should have a date on here. I'm very bad with dates. So this paper was published in 2013, and another group had found 4 more bursts that looked just like the Lorimer burst. And when we first heard about this discovery, we were so happy because we really wanted the Lorimer burst to be real. And the community was, really doubting that it was real. And then 4 more of them were found. So these 4 were also found with the Parkes telescope in Australia. You can see the pulses here. None of them were as bright as that original Lorimer burst, but they're clearly not noise. We don't have the dispersive sweeps on there, but they're really convincing. They're definitely part of a completely new astronomical population. So this was very, very exciting. The plot on the left here shows this dispersion measure quantity. So basically, the number of electrons the signal has traveled through versus galactic latitude. So this is how high above the plane of the Milky Way galaxy one is. And the red things are all the pulsars. And the blue things are these bursts that were found. And you can see they're complete outliers. They have much, much higher dispersion measures than one would expect if they were part of the pulsar population in the galaxy. So this was very convincing and showed that there was a completely new class of sources found. Exciting. And the periton mystery eventually was solved. So at the time of that Thornton et al. Paper, it still wasn't clear what these peritons were. We knew they weren't part of these fast radio bursts. And then Emily Petroff, who was a PhD student at Swinburne at the time, made a really interesting discovery. She looked at the times of day that these peritons, these masquerading bursts, were emitted, and she saw that they were all, okay, this cursor is like, I've got to go a different way than I think I need to go. Okay, so I think the purple events here are the real fast radio bursts. So the Thornton et al. Bursts, our bursts, other fast radio bursts, these purple ones here. And if you look at the purple ones, this is time of day. You can see they're distributed pretty evenly throughout the day, which makes sense because astronomical phenomena don't really know about the time of day on Earth. However, the peritons in purple were emitted all around lunchtime. And eventually it was figured out by Emily and some other folks at Parkes that it was due to a microwave oven that wasn't properly, sealed. So people would like open the microwave and it would cause this radio signal to be emitted. So these peritons were actually due to a microwave oven, which is kind of a good lesson for everyone here in Green Bank, I guess. This is why it's so important to have a radio quiet zone and have things like microwaves and Faraday cages where radio emission can't escape. Okay, so that's kind of a fun story. Okay, so I'm going to just present a few more slides about sort of the history, after the discovery of those initial bursts. We knew they were real. And then Dunk's going to finish up with like what we know and what we think they might be. Well, it's not really that important that you see the words. So in 2016, so until 2016, all of the bursts that had been found with Parkes, which is a little strange and a little worrying. Like, why are they all found with just one telescope? And all of them had just been a single event, just one burst, point at that position on the sky, never found anything else. In 2016, we found a burst that repeated, right? So we just detected a fast radio burst. It looked like all the others. And then we did the normal thing. Let's go back and look at that position on the sky and see if we see anything else, totally expecting not to see anything else. And lo and behold, many more bursts were detected from the same position on the sky with this Arecibo telescope. So this is the first, what we call, repeating fast radio burst. And this was a huge moment, right? Because if you think back to some of the ideas that Duncan had talked about for the origin of these bursts, one of them was two stars colliding. Another one was a star exploding. Well, those things would happen once, and then the source would be destroyed, and there'd be no way to ever produce another burst, right? Another thing he suggested was a neutron star, like some strange kind of pulsar, could produce multiple bursts, right? Because the source doesn't explode at the moment in order to produce this burst. So this ruled out things like explosions and stellar collisions, at least for these kinds of bursts. There might be some that don't repeat, but for the ones that repeat, it has to be some kind of neutron star or something that we haven't thought of, maybe something else, but a source that persists. This was a really important discovery. This was also really important for another reason. For all of those other bursts, we would see it once, that's it, and then we could never follow it up. We could never go back again and say, hey, let's detect it again and make a picture of it, or look where it came from with a better, more accurate telescope. This repeating fast radio burster, though, allowed us to go use the Very Large Array in New Mexico. This is another telescope that the National Radio Astronomy Observatory operates, just like the GBT. And because it repeated, we could use this telescope to sit on the position of this burst. And the VLA can make images. So with a telescope like the GBT, you just have a kind of big beam on the sky, and you can't really pinpoint exactly where something's coming from. This Very Large Array can make very precise images. So we went and used the VLA, and we just sat there making an image with very high resolution and waited till we saw a burst, and then we could say, oh, it came from there. And then we were able to localize it exactly to a galaxy. So on the right, you can see an optical image of the sky, and that red circle shows the galaxy that this burst came from. And that was really exciting because it was another step towards determining what is causing these things. We could say now it's coming from a particular galaxy. We could measure what we call the redshift of this galaxy. The universe is expanding. And from looking at something called the redshift, we can figure out how far away this galaxy is, like how redshifted the light is due to this expansion. And we found that this was coming from about 2 billion light years away. So really cosmological, not anything close to the Milky Way galaxy. We could also tell what kind of galaxy it was. It's a galaxy with a lot of star formation, so a lot of like young stars. So this pointed towards some kind of interpretation like a neutron star. So that was exciting. And then we expected all of them will look like that, right? So we found this one, it's in this star-forming galaxy. All the rest of them will be from the same kinds of galaxies. And unfortunately, the picture has not been so simple since then. Well, unfortunately or fortunately, it's not a simple picture, but it's also really interesting because we haven't solved the puzzle yet. So now there are a ton of fast radio bursts. The CHIME telescope in Canada, there's a picture of it down here on the right. And if you walk through the site here along the way to the GBT, you will see one of these kind of like U-shaped things. You'll see one of these CHIME dishes here, actually, and it's an outrigger of this telescope in Canada. Anyway, so this CHIME telescope in Canada is detecting about 3 of these a day, which is really amazing if you think about, sorry, I'm trying to get rid of that. If you think about the fact that it took us like, 4 or 5 years to detect another one after that initial FRB. And the reason it's detecting so many is it observes the whole sky, a huge area of the sky all at once. So it's catching all the ones that go off. About 10% of them so far repeat. So most of them don't repeat, some of them do. And there's enough that repeat that have been able to be followed up to figure out like what kind of galaxies they're coming from. Some of them come from things like the Milky Way, like this galaxy on the lower left there, a spiral galaxy like the Milky Way. But some of them come from very different types of environments. The one on the right, this image on the right, is the location of another fast radio burst, which came from something called a globular cluster, which is a very old cluster of stars, like very offset from the galaxy. So lots of puzzles, lots of different types of galaxies and origins. There's also some interesting evidence that we might be dealing with 2 different classes of fast radio bursts. So the properties of the ones that repeat look a little different from the properties of the ones that don't repeat. So this plot up here shows the bandwidth of the burst. So basically the frequency range over which we detect one of these bursts. And the x-axis up there shows the duration, like how long the burst is. And the different colors are repeaters and non-repeaters. And I think the orange ones are the repeaters and the green ones are the ones that don't repeat. And so the ones that repeat emit over narrower bandwidth ranges and they're a little bit wider. And the ones that don't repeat emit over more of the radio band and they're a little broader. And there's some pictures at the bottom here which show examples. So the one on the left, that one is a non-repeater. It's kind of a boring looking one. It looks a lot like the original Lorimer burst, which didn't repeat. The ones on the right are bursts that have repeated and they look way more interesting, right? They emit over only a little bit of the range and frequency. They have very odd kinds of structures, like very interesting structures. So it may be that there are 2 different sources for fast radio bursts, 2 different kinds of objects that are producing these signals. Okay, and I think this is maybe my last one before I pass it off to you. And then another really interesting part of this puzzle was solved a few years ago when a fast radio burst was detected from a magnetar in our own galaxy. So magnetars are very highly magnetic neutron stars, so like pulsars, but with way bigger magnetic fields. And we know of about a dozen of these in the Milky Way galaxy. And a fast radio burst, and I'm calling it a fast radio burst, but it wasn't nearly as bright as these ones from other galaxies, but much brighter than a pulse from a pulsar, came from one of these magnetars. And it was detected with CHIME, and you can see the CHIME plots on the right. And it was also detected with this very small telescope called STARE-2 in California. And so this was a really interesting piece of the puzzle because it showed that at least one really bright burst was detected from a very highly magnetic neutron star. Are all of them produced by these magnetars? We're not sure, but we know at least one is associated with a magnetar. Oh, I have one more slide, I think. And now many of these fast radio bursts have been localized to galaxies. So these are optical images of galaxies in which fast radio bursts have been detected. And the main point of this is just there's a huge diversity in the kinds of galaxies they're coming from. Many of them are star-forming galaxies, so galaxies with lots of young stars. Rarely what we call red and dead galaxies that aren't making stars anymore. Some of them come from in the spiral arms of the galaxy, some of them come from far outside the galaxy, and all these little circles are the localization regions of these fast radio bursts. So this is like the next big thing, detecting more of them and figuring out exactly where inside the galaxies they're coming from so we can figure out what kind of sources are producing them. And this CHIME outrigger here at Green Bank is going to really help with this. CHIME right now can't localize these fast radio bursts very precisely, but with a telescope in Canada and another one all the way here in West Virginia, it's going to be able to pinpoint the source of these fast radio bursts, or at least the location, much, much better than it can right now. So I will pass it back to Dunk to finish off.
Thanks very much. Yeah, so the story is definitely continuing, as Maura said. There's lots to be done. One of the really exciting things, in addition to all of these pulses that are being found by CHIME, is like how far away can we see these FRBs? How early in the universe's history were they produced? So you might be wondering, well, what's the most distant one that's been seen so far? It came out late last year. This burst has been tracked to a galaxy whose redshift has been measured. And from that redshift, the distance to the galaxy turns out to be 8 billion light years away. And it's an incredibly luminous burst in the duration of a few milliseconds that we observe. The equivalent amount of energy is what the sun puts out now in 16 years. And so this is kind of right at the cusp of what some of these neutron star models can do. So it's really starting to push that, which is very interesting from what type of sources are they point of view. But the other thing is, like, it tells us that we can probably see more of them further out in the universe if we just keep looking and keep our eyes open. And that's because the universe, we all love the story about time machines and want to get in one ourselves perhaps and go back in time. But astronomers are very lucky in that our whole work is really based upon the fact that we're observing the universe at different phases. As we look to sources that are farther and farther away, we see them in a phase of the universe as it was earlier in time. And so this is just a nice image from the National Science Foundation that kind of traces the evolution of the universe back over the 14 billion years or so that it's been in existence, all the way from the Big Bang there at the bottom right, where the universe was very small and very hot, to when the first stars were formed, and the black holes and other sources were formed shortly after that. Then the universe went through a period of what's known as reionization before the galaxies that we see today begin to emerge. So we're seeing fast radio bursts out to 8 billion years back into the past. But how far? If there perhaps there are some fast radio bursts out in this earlier epoch that we just haven't seen yet that probe the earlier epochs of the universe when it was being reionized. And so that's a real ongoing work. And so that really requires telescopes of the highest sensitivity, like the GBT, for instance, or like the CHIME telescope, or perhaps the FAST telescope in China is the world's most sensitive telescope. So those could potentially see those really distant sources. So we have a number of experiments underway to look at those, which is really exciting. One of the things that FRBs might be able to do, and they're already doing quite a good job, is they're able to measure the Hubble constant. For those of you that follow these things, the Hubble constant is the expansion rate of the universe, dating back to Hubble's measurements around a century ago. We're already, with fast radio bursts, able to measure the Hubble constant. Here's what you can do with fast radio bursts right now. This bar gives you quite move the mouse in the right direction like Maura. The bar gives you the extent of the uncertainty in Hubble's constant determined just from fast radio bursts right now. And it's not as good as some of the measurements that are out there in the literature. But over the next decade, as more fast radio bursts are found, that error bar should shrink, and we'll be able to use fast radio bursts as an independent check on the Hubble constant, which is a fascinating part of the astronomer's toolkit. So there are lots of things to do, and this, we could talk for a whole hour about the points on this slide. I just want to highlight a couple of things here that there are really many things that we want to learn about FRBs. As Maura mentioned, we don't know whether there are multiple classes, or whether they really do all FRBs repeat yet, or the ones that we've only seen once, have we not observed them long enough? Some of the FRBs actually show some form of periodicity associated with them that are actually they're periodically active on time scales of several days and tens of days in some cases. And perhaps there's some binary orbit that's driving that behavior. What I think is particularly exciting is some of the other parts of the electromagnetic spectrum, or perhaps with other observatories like those in gravitational waves, where we could observe a counterpart with a fast radio burst in the radio and a source elsewhere in the electromagnetic spectrum at the same time. That hasn't been done yet, apart from that source in the Milky Way that Maura mentioned. And so there's a lot of potential for discovery there. So lots of work to do. This is, you know, part of an effort of a huge team. You know, we as scientists are, you know, are just eternally grateful for the support that we get here in the US and around the world with our colleagues. And that's due to a large extent for a lot of our support comes from things like the National Science Foundation, which relies on tax dollars to fund them. So we are always eternally grateful for you, the taxpayer, to support this work, which really wouldn't happen without that support. Also here in West Virginia, we have the university, of course, and the observatory here, and the West Virginia Space Grant Consortium, which is funded by NASA. And our many collaborators and colleagues throughout the world. Matthew Bales, our fellow laureate, Ronnie Crawford and Nash Narkovic, also on the discovery paper with us, and our students and colleagues and postdocs, from which we are so grateful for, and we learn so much throughout the years. So thank you for listening to this story, and you know, we're just so happy to be able to share it with you. So yeah.
Thank you both. I'd like to take some questions, and we do have an audience online as well, so I think we'll take a couple of questions in person and bounce back and forth if that works for you, Jacob. All right, excellent. So ask away. What questions do you have?
I'll ask a question on determining the Hubble constant with these. I mean, there's not a standard luminosity, or how do you get an H0?
Would you mind repeating the question in the microphone?
Yes. So Dave is asking, how do we determine the Hubble constant using fast radio bursts, if given that there's not a standard luminosity? So we do that from the FRBs that have host galaxy measurements, distance measurements. So we have the redshifts of the host galaxies, and we have the dispersion measures of the fast radio bursts. Yeah. So we combine those two, and it's basically a statistical measure. The more that we have, the better things get. So it'll eventually, you know, get really good, you know. Yeah.
Are there plans for a third chime? Because I'm thinking of degrees of freedom.
Yeah, there are, right? I mean, there's an outrigger here at Green Bank, and there's going to be another outrigger in Canada.
Yeah.
Is it Northern California? Yeah, there's a Hat Creek, right? Hat Creek, that's in California. Yeah, yeah, but that's a great question. Yeah, so with 3, this localization will be way more precise than with the 2 that we have now. And we're excited to see what it'll do. It's not quite up and running quite yet, so we haven't really been able to reap the benefits of that yet. But once that system is going, it's going to be amazing, because for every one of those FRBs, you know, multiple of them every day, we'll be able to figure out exactly where they're coming from.
So the different sources that came from microwave, right? Why do they show that dispersion curve? If they are like from
the microwave?
Yeah.
I don't know. Do you know exactly why they do that? I mean, I think it's just some.
Yeah, I think it's related to the slowdown of the magnet itself.
Okay.
Yeah.
Yeah. Like the magnet in the microwave.
Yeah.
So as the microwave shuts off,
yeah,
the magnet slows down and makes that.
Right.
Okay.
We have an interesting question online. Could a neutron star, quote unquote, swallowing a planet generating that part?
Yeah. I mean, something weird would have to happen.
Right.
Like, I don't think just the gravitational swallow of this planet is, you know, would produce enough energy, just like kind of the mass of the planet. But maybe if the planet got ripped up and all the particles got accelerated in the magnetic field of the neutron star and produced some like really bright burst of emission, maybe. There are hundreds of papers on different origin methods for FRBs, and that one may exist. there are so many of them. Sue Ann.
The FRBs that you found host galaxies for? Are those all repeating FRBs?
Yeah, so the question is, were the FRBs in host galaxies all repeating? And the answer is no, they're a mixture. The repeating ones were initially easier to see because they repeated, and so people were able to localize those first. But then as the arrays have gotten better, being able to observe the one-offs, obviously just once, but good enough to localize them. So we have a mixture now, and there's about 40 or so that have been localized to host galaxies now. And so there are, I want to say about 30 of those now, I think, are one-offs. It's quite a high fraction now.
You said that they were all from star-forming galaxies. Is there any sorting property for those 40 at all, or are they just all over the place?
I mean, the repeaters and the non-repeaters, there's not a real clear differentiation in the kind of galaxies that the repeaters and the non-repeaters are coming from. It would be really nice if like the repeaters all came from star-forming galaxies and the non-repeaters all came from old galaxies, but so far that doesn't seem to be the case.
And there are some found in globular clusters as well. Or there's one, at least so there's one FRB that's seen in a globular cluster of a nearby galaxy, which is very strange. You wouldn't expect star formation to be happening there.
Yeah, it's been really exciting because we kind of saw the pulses from this magnetar. We thought, okay, they're all from magnetars. That's great, but magnetars are born from young stars. And then one was found in this globular cluster, and you can't have a magnetar in a globular cluster. I mean, that would be really weird. So every time we think we understand it, then there's a new discovery that turns everything on its head.
Is there a reason why distances are sometimes quoted in light years and sometimes in parsecs?
We tend to, when we're giving a public talk, we use light years because people have more of an intuition for that. But then when we're writing papers, we put them in parsecs. Yeah, that's generally what happens.
Is it true that a parsec is roughly around 3 light years?
That's correct. Yeah. Yeah. So every time I give a talk, I'm like doing the multiplication by 3 in my head, and hopefully I get it right.
Right.
So over the last what is the most surprising thing since the discovery that first you've seen kind of analysis? Or most surprising, or just like the most exciting?
I mean, for me, it was probably being part of, I mean, the original discovery was obviously the most exciting, but being part of the team to find the first repeater, because we really, by that time, had just accepted these were all one-offs. And I still remember the email, this P Alpha team email, where a grad student looking at the data had found these repeated bursts. And I just remember being completely flummoxed. And then probably the second most surprising thing is when he announced that, I thought, oh, for sure, now we'll find an underlying periodicity, right? Not that it's repeating, it's going to be real easy to find this underlying periodicity, just like these were pulsars. And that was extremely surprising. I spent a really long amount of time using these same codes that we used to find the periodicities in those sporadic pulsars. And it was really surprising that they were so different. We couldn't find any. What about you, Dunk?
Sorry. I think one of the most exciting ones recently was that discovery in a globular cluster. That's really got a lot of people thinking and trying to find out ways to perhaps form magnetars in globular clusters through smashing white dwarfs together and things like that. So yeah, and so it's opened up a lot of interesting ideas for how to find them as well.
We do have another question online. I think we'll take next.
So yeah, the other question online is, has gravitational lensing been observed with FRBs?
And could you repeat again? I'm sorry, just so the folks
online. Oh, the question is whether gravitational lensing has been observed with FRBs. I think the answer is no.
Do you think that is there an energy limit from FRB or the distance limit we can use for FRB to do cosmology?
So the question is, are there energy limits or distance limits we can use for FRBs to do cosmology?
Yeah, first
Yeah.
one is energy limit.
Yeah.
And if it's limit, then probably is corresponding to a distance limit.
Yeah, so we can measure the energy we detect at our telescope. And if we can get the distance from observing a galaxy and measuring its redshift or how fast it's moving away from us, then we can convert the energy we measure at the telescope into an actual energy. And those are the things that are, well, the distance is really what we need to do cosmology, but the actual energy is really important for understanding what kind of source could produce it.
So for those FRB survey, do you think it's a better strategy to do very wide field but shallow survey, or pointing towards the direction but do really deep survey?
That's a great question. I mean, I think both
Yeah.
is kind of the answer. I think to do stuff like the Hubble constant experiment that Duncan talked about, you really just want a lot. Like you want as many as possible because you want to average over all the variables, like how much of the galaxy the pulses travel through, right? You want to like just average over a whole ton of them to actually learn about the intergalactic medium. But if you want to probe it out to large distances, then you need to sit and stare for long amounts of time. So I guess kind of both. I mean, I think finding individual distant ones is very exciting, but I think the most cosmological kind of bang for the buck is going to be like wide field, but shallower, where you just detect a whole ton of them. I don't know.
Yeah, I mean, I think that's right. And some of the interesting things that are happening now are we're seeing FRBs in nearby galaxies, and so why not just target those really deeply? And you might see some fainter sources that have been missed before. So that's one thing that we're pursuing with the GBT.
Yeah, and with the 20-meter telescope here, a smaller telescope here, we're trying to get funding to use that just to stare at nearby local galaxies just for kind of all the time, just look at them for really long amounts of time. And even with a small telescope, we could detect bright bursts from those galaxies.
Have you seen any correlation, especially with repeating fast radio bursts, gravitational waves, or are there any papers out there addressing that?
There's one, yeah. So there's one that's been proposed. So the question was, have you seen any correlation with repeating fast radio bursts and gravitational wave sources? It's actually, I think it's a, I think it's a non-repeater. Yeah, that's right. I think so. So there's a single chime FRB has been recorded, and it's close to a gravitational wave event in time. The problem with a gravitational wave event is it has a huge error circle on the sky. Tantalizingly, though, because you can, from the gravitational wave signal, you can infer the distance quite well, and it matches up with the DM of the FRB pretty well. The dispersion measure that we see in the radio. So that there's sort of tantalizing evidence, but it's not strong enough to claim a detection. I think it's kind of like a little bit ahead of its time. As the gravitational wave observatories are, they're now being, turned on again with greater sensitivity than before, and all these radio surveys that are going on, I think we'll see more examples of those. So yeah, I'm very excited by that possibility.
Any last question from the audience? Just to follow up on the last question. That Jordan, was it from a black hole neutron star or like two neutron star?
I think it was a double neutron star merger candidate in the gravitational wave event.
Yeah. So it would make sense. Would hang together. You might expect something like this from one of those, but I think it's not really that believable statistically, unfortunately.
Yeah. It's a good test case at the moment.
All right, that's it. A final thank you. I'm going to mooch in on the microphone very quickly here just to thank our online audience for joining us. Thank you all for coming. Don't forget about the reception out front. And I also just want to add that the story of fast radio bursts and the ongoing research is one of my favorite stories to tell on our public tours. because it reminds everybody that science is all about exploring the questions that we don't have the answers to yet. And so many of us, the way we learn science in school, kids come out with the impression that the job of a science is to sit around and know everything, right? But the job is actually to use the things that we know to keep figuring out how we can learn about the things that we don't know yet. And this story just really does that powerfully. So I am excited to see where the research goes, and thank you so much for bringing it to us today. So thanks, everyone.